Hello, everyone, and welcome to the CosKASI ECR seminar. It's a great pleasure for me to introduce our speaker, Vicky Fawcett. Vicky recently finished her PhD at Durham University and is now working as a postdoc at Newcastle University. Today, she will share her research on red and extremely red quasars in DESI, strong link between dust and radio emission. Vicky, please start when you're ready.
Great, thank you. And yeah, it's great to be here virtually. And thanks for inviting me. So yeah, I'm a new postdoc at Newcastle University, and today the work I'll be presenting was predominantly during my PhD at Durham University, working with Dave Alexander and the DESI Galaxy Quasar Physics Working Group. And I'm going to talk about red and extremely red quasars, but I will get on to what they are in a bit. So a little bit of background. Hopefully everyone here has some idea of what a quasar is. They're also known as quasi-stellar objects, or QSOs, and they're extremely luminous types of active galactic nuclei. So AGN being this supermassive black hole in the center of a galaxy, being fueled by this accretion disk, this very bright disk of matter that's incredibly powerful, and we can see them across the whole electromagnetic spectrum. And the majority of quasars have very blue optical colors, and this is because with a quasar, we're viewing this accretion disk straight on, which is why we see broad lines as well as narrow lines. And this accretion disk is a black body spectrum, and it peaks in the UV and optical. So majority of typical quasars are very blue, and this is predominantly how they're selected in quasar surveys. So just because I'll be talking about quasar spectra, because that's what DESI is all about, here I've just shown a composite from the Sloan Digital Sky Survey of a few tens of thousands of kind of typical quasars. So you see here you have this rising blue continuum up towards the UV rest frame here. And then on top of this continuum, you see these very broad emission lines, such as magnesium-2 and H alpha. So this is kind of what a typical quasar spectrum looks like. So the reason people really like to study quasars, or one of the reasons, is in the context of galaxy evolution. So we know that there's this observed M-sigma correlation. So this is a tight correlation between the mass of the supermassive black hole and the stellar velocity within the bulge of the host galaxy. And even though the supermassive black hole and the host galaxy are on vastly different scales, this suggests that there's some kind of intrinsic link between the growth of this central supermassive black hole and the surrounding galaxy. So a lot of people have been looking into how we can kind of co-evolve galaxies with their supermassive black holes. And one kind of idea of this growth phase starts with this idea of gas-rich major mergers. So these came out of kind of very famous simulations from Sanders and Hopkins, where if you start with a merger here, you push a lot of gas into the center of these merging galaxies. And this obviously is a very energetic phase, and it creates a lot of star formation. So you have this extreme obscured star formation phase, which some people think are ULUGs, so extremely luminous infrared galaxies. But then this also ignites a quasar just because you have so much gas falling into the central supermassive black hole. But what people think is before you get to the kind of fully fledged quasar phase, this typical blue phase, we have this intermediate, what people are calling blowout phase. And this is quite a short-lived phase which is in between this extreme starburst and this blue quasar unobscured phase, where we think this is some kind of dusty quasar that has powerful winds or outflows, hence the name blowout, which then blows away the dust and the gas, revealing this unobscured blue quasar. So what I'm interested in, what is quite a big topic at the moment, is what is this blowout phase? What is this kind of key connecting phase between this starburst and this the quasar. And if we knew this, this would really help us with these models of galaxy evolution. So a number of kind of, I guess, slightly exotic and a lot of acronyms have come out for different types of dusty quasars that could be this transitional phase in the evolution of quasars. So I'll just go through a few of the popular ones. So sorry if I don't name your favorite kind of dusty quasar. So first of all, the kind of well-studied red quasars. So these are simply just quasars that are selected in the optical or the infrared to have very red colors. And I've listed a bunch of references, and as you'll see, a lot of them are from our group in Durham, since we've been very interested in these red quasar objects. And here I've just shown a composite that I'll come back to this data later, where again, in blue, we see this typical blue quasar, and then in red is a red composite. And you can see that the red quasar looks remarkably similar to the blue quasar. We still see these strong, broad emission lines. We're not obscured, we're not type 2 AGN, but you see that instead of rising towards the UV, we have this turnover in the spectrum. And this kind of frequency dependent turnover is indicative of dust reddening. But again, I'll come back to that. And like I said, a lot of work within our group at Durham has been on red quasars. And I thought this is just a very nice schematic, so I thought I'd show it from a former PhD student, Ms. Elke Clint, where she has, in her 2019 paper, she does argue that red quasars fit quite nicely into this evolutionary scenario. And this is just a kind of prettier version where red quasars are in between this starburst and blue quasar phase. So you also have things called extremely red quasars, or ERQs. And how these are different to normal red quasars is that they're selected to have very red optical to mid-infrared colors. So two kind of famous papers that looked at ERQs in SDSS are Ross and also Fred Heyman's 2017 paper. And here I'm showing some more composites from Fred Heyman's paper. And these quasars were selected to have very red I minus W3 colors. So I being an optical band and W3 being mid-infrared. And what you can see, the different colors just show different amounts of I minus W3 reddening. There's 3 different bins, and there's almost no flux at the optical UV end. But you see these extremely kind of strong, and they argue quite peculiar emission line profiles. And why ERQs were a very hot topic, and I'll obviously get back to them with my DESI study, is that they're some of the most luminous quasars, but also the most powerful outflows ever recorded in quasars have tended to be recorded in these ERQs. So they're known to be red, they're known to host powerful outflows. They're a strong candidate for this transitional phase. You then get kind of more obscured things. So for example, dust obscured galaxies, or DOGs, or in particular, hot dust obscured galaxies, hot DOGs. And these are selected in, to be honest, quite a similar way to ERQs. They are selected to have very mid-infrared colors, but they're often selected on the what's called this kind of WISE dropout selection. And I kind of illustrated this here. Here are the 4 bands of WISE, which is this mid-infrared survey, so 3.4 microns up to 24 microns. And you can see in W1, there's, I would guess, barely a detection, if any. And then you get up to W3 and W4, the longer wavelengths, and you see a very strong detection. And they're also, in addition to this WISE dropout, they'll also be selected to have very red, either W2 minus W3 or W2 minus W4 infrared colors. And again, here's some of the kind of famous papers looking at hot DOGs. And this is kind of a nice little SED comparison from Ms. Elke Clint's thesis, where in this blue up here, you can see this is a typical blue quasar. So it looks similar to our composites earlier, where you see this rising blue continuum, and overplotted are these strong emission lines. This blue line here is the same blue quasar plus some amount of dust. So again, this would be our red quasar. Then in the black is our ERQs, so extremely red quasars, and you can see that they are red, but compared to the reddened quasar, they have a much flatter SED. So again, I'll get back to this, but some suggest maybe it's not simple dust reddening that makes these objects red. And then in orange here, you have the hot dog. So basically what you see with hot dogs is that you really rapidly drop in flux as you get to bluer wavelengths because of this Weiss dropout and extremely red colors. And finally, I'm just going to throw in, there's these things called broad absorption line quasars, or BAL QSOs. And these guys are selected to have very broad absorption troughs that are blueward of some of the UV lines. And in particular, they're often selected on the carbon-4 line. And these absorption troughs, they indicate there's very powerful winds in these systems. So here are some composites that I created actually using DESI data, because I'm also quite interested in BAL quasars. And the different colors are different bins of balnicity index. And balnicity index is just a measure of the strength of the wind. And what we see is that as you bluewood of the carbon-4, silicon-4, and Lyman alpha, we see these strong absorption features, which shows that there's winds in these systems. So obviously, since these are systems known to host powerful winds, and they'll have other properties I'll refer to a bit later, again, they're thought to be an interesting population in context of this blowout phase. So something I'd be quite keen to do during my postdoc, but we'll see if I get around to doing this, is, as you see, there's these 4 different types. There's more actually of these exotic kind of acronyms in quasars. And some of them have very similar or just very specific selections. And it's my opinion that there's probably quite a lot of overlap between all 4 of these objects. And it would be pretty cool to have some kind of unifying model of these dusty, windy quasars. Instead of all these different unique teams with their favorite type of objects, just spending 10 years looking in particular at that object. But I'm happy to discuss that if anyone thinks that's a terrible idea. So that's just a little bit of background. In this talk, as the name suggests, I'm going to focus on red and extremely red quasars, since this is kind of what I've been focusing on. So how I'm kind of splitting the talk up is the first half is going to be looking at red quasars in SDSS. So this is the work predominantly done in my PhD and from my other group in Durham. And then I'm going to move on to red and extremely red quasars in DESI, which is something that I'm still working on at the moment. So during my PhD, we looked at red quasars in the Sloan Digital Sky Survey, SDSS. How did we select our red quasars? So in our group, we go for an optical selection. So this is demonstrated by this plot, where we select red quasars as the top 10% or the reddest 10% of the G-I optical color. And we do this in a redshift dependent manner, as you can see by this plot. And we also restrict to redshifts up to 2.4 or 2.5 to make sure that the Lyman break is not affecting the optical color. And then importantly for a lot of the work we're doing, because we were really interested in just comparing red and blue quasars, comparing their properties to try and test this red quasars as this transitional phase, we select a control, or I'll also just call them blue quasars, as the medium 50%. So these represent typical quasars, and since we've selected them in a consistent way, it means that we can robustly compare the 2 samples. And for a lot of the work I'll show, we also match in redshift and luminosity. And it's especially important to match in AGN luminosity when you're looking at these dusty quasars, because since they're red, they're slightly obscured, especially in optical surveys. If you didn't match luminosity, you'd get a bias towards higher AGN luminosities for the red quasars compared to the blue, just by selection effects. And actually, something that I'm very interested in looking at is for example, these ERQs, these hot dogs, they're incredibly luminous objects, but most of the time this is just due to a selection effect. And it would be interesting to know kind of what their properties were compared to the overall quasar population if you actually match in luminosity and you take away luminosity as a factor. Okay, so the first thing that we looked at when we compared red and blue quasars is their radio emission. So here I'm showing some work from this 2019 paper from Lizalka Clint that I mentioned earlier. And she looked at the first radio properties of SDSS red and blue quasars. So first is a 1.4 gigahertz radio survey at 5 arcsecond resolution. So the two kind of key results that she found in her paper was, first of all, she found a factor 3 higher radio detection rate in the red versus the blue. So this is detection fraction versus in bins of redshift. And here you can see the red quasars are above the blue quasars for all redshifts. Just to note here, we have blue and control, and this is just because in Lizalka's paper, she also selected the bluest 10% of the quasars to compare, but she didn't find any difference between the bluest 10% and the middle 50%. So in later papers, we dropped this, this blue sample. Looking at radio counterparts, she also found that red quasars show a preference for faint, where we can't really say anything about the morphology, or compact, so unresolved at the resolution of the radio survey counterparts compared to the blue quasars, which is shown here. But if you look at more classical extended or these double lobed like FR2 systems, we find no difference in the fraction of red and blue quasars. So in some follow-up papers by myself and David Rosario, we also showed this radio emission is radio quiet, radio intermediate. So the enhanced radio emission peaks around this radio quiet threshold. And we actually use much higher resolution radio data to show that the red quasars are actually have radio emission compact down to host galaxy scale, so about a few kiloparsecs. And this was interesting because the radio emission shouldn't really be affected by dust, and it shouldn't really be affected by orientation. If anything, you might expect the blue quasars to be more enhanced in the radio if we were just viewing blue quasars more face on and say red quasars more through the dusty torus because of Doppler beaming from the radio jet. So this kind of early work suggested there's some real fundamental differences between red and blue quasars. Red quasars seem to be intrinsically different. It's not just the fact that they're red. So the next thing we looked at was kind of what was the cause of this radio emission, and what we found is that it wasn't due to star formation. So we found between red and blue quasars, no differences in the star formation properties. And this was nicely done by Gaby Calistro Rivera in her 2021 paper, where she created composite SEDs for SDSS red and blue quasars. And she found that they were remarkably similar, apart from over here, which is the UV optical end, and this can be completely accounted for by dust. So she found no differences in the star formation rates between red and blue quasars, and this is also backed up by some preliminary unpublished ALMA data we have, and also my 2020 paper as well. So like I said, this suggests that the radio emission is driven by AGM processes. So either small scale young jets, which could fit into this kind of evolutionary scenarios. Maybe the reason that they're very compact is because they're small jets that just haven't had the time to grow into these very large jets, or frustrated jets or winds driving shocks in a kind of dusty environment, which again would produce quite compact radio emission. So I've been telling you that red quasars are probably red due to dust, but in my 2022 paper, we used VLT X-shooter spectrums. This is very nice kind of intermediate resolution, but wide wavelength spectroscopy. And what we found was that red quasars are consistent with dust red and blue quasars. And that's what this kind of movie is showing. What we did is we took this, the blue is a blue quasar composite from our X-shooter program. And in red, you're seeing it was only 12 red quasars we observed with X-shooter. And then in gray is this blue quasar composite plus some amount of dust that I'm showing in the bottom right. And hopefully you'll be convinced that just simply adding dust to this blue quasar, we can actually recreate the spectral shape of the red quasars remarkably well. And just to know, these were really modest amounts of dust extinction. So as you can see, only an AV of up to about 0.6 mags, which is equivalent to an EB minus V of up to about 0.2, 0.25. And this is in comparison with some of what are called the heavily reddened quasar samples from Elliot Glickman and Manda Banerjee's group, who select their red quasars using near infrared. And they find AVs of up to about 2 mags. So these are very modestly reddened dust red quasars, yet we're still finding this kind of huge difference in the radio, which is interesting. So the other things we did with this X-shooter data was to look for differences in the accretion properties. So we thought that maybe if you had differences in the kind of central engine, the accretion properties of red and blue quasars, this may be what's driving the differences we see in the radio properties. But we found no significant differences in the Eddington ratio, the mass accretion rate, or the black hole masses, although we're obviously limited on source statistics. But this does suggest that it isn't differences in this central engine that's driving the enhanced radio emission. We also looked for differences in the outflow properties using the O3 and the carbon-4 line, because these are the kind of commonly used emission lines people use to trace outflows. And we looked for differences out in the outflows because, as you remember, this blowout phase, it kind of predicted that there would be powerful outflows in order to blow away the dust and the gas to reveal this blue quasar. So in our work, we didn't find any significant differences, although, again, we are limited to 12 red quasars. And I do want to note that in our previous work, so the work by Gabi Calista Rivera, she looked at the O3 outflow properties for a sample of redshift less than 1 SDSS red quasars, and she did find an enhancement in the outflows for red quasars. And we're also finding an intriguing link to low ionization broad absorption line quasars, or low BALs. So low BALs are just BAL quasars, but they have additional absorption features that, for example, blue would have aluminium free. So that's blue would have some more low ionization species. And we're finding a few kind of links between low BALs and red quasars. So low BALs also appear to be reddened on average, and they also have enhanced radio emission. And given the fact that low BALs are known to host powerful outflows, you could think that because they're connected, that red quasars are more likely to have these kind of BAL winds. But if you want to hear more about that, ask me afterwards. So just to wrap up from this kind of first half, so how are SDSS red and blue quasars different? Well, we find that they have this enhanced radio quiet radio emission that's on nuclear galaxy scales. And we find no differences in the star formation properties or the overall SAD properties of red and blue quasars, other than accounting for dust. And we do find that dust is the main cause of reddening in these red quasars. We also find no significant differences in the accretion or outflow properties, although we're limited on source statistics. So far, we think that in red quasars, the enhanced radio emission is likely due to winds or frustrated jets, causing shocks in this more dusty environment. But the issue we have with these previous studies is that we're limited to the depth and also the quasar selection of SDSS. So in order to really explore the relationship between red and blue quasars and to place red quasars in the context of this galaxy evolution model, we need to expand our parameter space. So we need more obscured red quasars, since with SDSS, since we're magnitude limited, we're really only selecting the tip of the iceberg of reddened quasars. Like I said, they're very modestly reddened. And we also need to push to fainter systems. And as you'd guess, DESI is kind of perfect for doing this. So I'm sure everyone here has probably heard of DESI. I know a lot of people at CosKASI are doing work on DESI. So DESI is the dark energy spectroscopic instrument, and it's aiming to measure the spectra of over 40 billion galaxies and 3 billion quasars over a third of the sky. And it's on this male 4-meter telescope at the Kitt Peak National Observatory. And obviously the main focus of DESI is to constrain possible models of dark energy, that's in the name. But obviously if you have 3 billion quasar, there's a lot of science you can do, and that's where we come in. So within DESI, our group have a secondary target program. So these are programs in DESI that utilize spare fibers, and our program, we're trying to select dust-reddened quasars in DESI that might have otherwise been missed by the nominal quasar selection, which is obviously biased towards the majority of these blue quasars. So I just want to briefly run through the target selection. So we start off with the DESI Legacy Survey Data Release 9 photometric catalogues, which I've linked here. We then do a bunch of cuts, including requiring the morphology to be PSF, like majority of quasars, and to have a signal to noise ratio of greater than 3 in the W1, 2, and 3 bands. And we do this because we then apply the Mateus 2012 AGN wedge selection. So for those that are unfamiliar, this is the Mateus wedge, is this region in W1 minus W2 versus W2, W3 color space that's been shown to be very efficient at selecting AGN and very good at having a low contamination rate from galaxies and stars. And just to note again, the wavelengths of these 3 different wavebands. We then decide to remove the main quasar color selection in DESI. So what I mean by this is within DESI, there's kind of 2 main ways that they select quasars. There's a random forest approach, and there's also targeting a region of color space where quasars are known to lie. And I've highlighted this on this plot here. So this is a region of G minus R versus R minus Z color space. So for our secondary target program, we said, I don't want you to observe anything in this box because we're going to get, thousands, millions of quasars in this box anyway. We want you to observe things outside because then we're more likely to get these rarer objects that are red. By the selection, we do, as you can probably see by this plot, get a bunch of objects that are incredibly blue, but this is only a small fraction. So those that do are removed, so lie outside of this main color selection, and also are targeted by our program, because you're going to get ones that satisfy this anyway without being targeted by our program. So have the bit mask of our secondary target program, we call our primary sample. And then for comparison purposes, we say actually we're going to take everything, including this main color selection, the ones in this main color selection, and we're requiring them to be targeted just by the nominal quasar selection within DESI. So these are kind of typical DESI quasars. And then this is what we're calling our nominal sample. And I just want to note the kind of data we're using in this talk and in my first paper that should be submitted soon, is using data from the early data release. So this is data that's going to be publicly available at some point next year. And using just the data from the EDR, we find about 3,000 objects in our primary sample and about 99,000 objects in this larger nominal sample. So the first thing we had to do when we got our primary sample is to visually inspect each of the spectra. So why was this necessary? So in a paper by Dave Alexander, my PhD supervisor, he led the effort on the quasar visual inspection within DESI. So there was a lot of visual inspection of the different target classes to understand whether our kind of redshift and spectral fitting pipeline was working. And what we found was that it is working very well. I think it gets the redshifts correct on over 99% of the quasars, but the ones that it didn't get right tended to either have strong host galaxy features or were reddened. So here I'm showing a composite from this paper where in blue are the ones that the DESI pipeline, we used red rock, got right. So you can see typical blue spectra, and the ones that it missed, it got wrong, shown in red. And you can see that they're more reddened, and the zoom in shows these strong features. So obviously, given the fact that we're trying to target reddened quasars, it's important that we visually inspect our samples so that we get correct redshifts and spec types. So these are the type of objects that are probably going to be failed by this red rock pipeline. So I went away and visually inspected all 3,000. I just want to note all the work here is preliminary because this is just based on my own visual assessment, and we're currently trying to add in a second and a third visual assessor in order to make this more reliable. But if you believe me, this is kind of the work I'll show. So here I'm showing a pie chart of the different spec types within our primary sample. The low quality section just shows the spectra that were either that essentially were too low signal to noise for us to accurately determine the redshift or the spec type. Then we have 5% stars, so only a 5% stellar contamination, which is consistent with the nominal DESI quasar selection. And then we find 60% are quasars, which are the ones that we're interested in. And on the right here are just some comparison plots where I have 6 micron luminosity, so the AGN luminosity, and the R band magnitude, both versus redshift. And then in the blue are the primary quasars from our secondary target programs, these 60%. And in the purple are the quasars from the nominal sample. And we got the spec types from the nominal sample just using the standard DESI pipeline, because the majority of these are going to be blue anyway. And then I've also shown the galaxies and stars from our program, which I'm less interested in because I'm a quasar person. And then again, for comparison, I showed the quasars in our sample that were also observed by SDSS. So these are the gray diamonds, if you can see. And essentially what this is showing is between our program and the DESI nominal program, we have very similar redshift and AGN luminosity distributions. But if you look in R band magnitude, we go much fainter than both the DESI nominal sample and also SDSS, which is what we wanted. Okay, so what we're really interested in is to look at red and extremely red quasars. So how we selected these from our sample, we started with our primary sample, and then we said they had to have a spectral type of quasar, and they had to have high quality spectra. So we have robust redshifts and spec types. We then remove any type 2 AGNs. These are AGN that don't show any broad lines, and also remove ones with either poor photometry or clearly had two objects in the same spectra, which will kind of mess up our fitting. Then to select red quasars, we do a very similar approach to what we did with our SDSS work. We start with our nominal kind of parent sample, and we then select red quasars as the top 10% of the G-R color distribution. We do G-R rather than G-I, simply because there's no I-band photometry in the legacy catalogs. We then use this sets a boundary of red quasars, and we use this boundary, this red quasar track, to determine how many of our primary sample are red quasars. So it's a little hard to see, but you can see the same track up here is on this bottom plot, which is with our primary sample. We also restrict to a redshift range of less than 2.5. And when we do this, we find that about 80% of our quasars are actually red quasars, which is Very, very nice. That's what we wanted. And something I found interesting is I also plotted in this dot dashed yellow line is the red quasar track from SDSS. This is taking SDSS DR16 and doing exactly the same approach here, taking the top 10% of the G-R color distribution. And what you can see is that the SDSS red quasar track is considerably bluer than our track. And actually, if you kind of counted the number of DESI quasars above this SDSS track, is actually like the top 30%. So this already shows that with DESI, we're pushing to much redder systems. To select extremely red quasars, if you remember, this is an optical to mid-infrared color cut. So to do this, we selected our ERQs based on the Z-W3 colors of the Heyman SDSS ERQs. Again, we use Z-W3 rather than I-W3, which was used in the Heyman paper because there's no I band. So this plot in the purple crosses are the Heyman ERQs from SDSS, and we simply use this as a kind of boundary to select our ERQs. And when you do this, this comes out as a Z-W3 of about 3.9 mags in AB. And we find about 38% of our quasars are extremely red quasars based on this definition. So I kind of hinted at this earlier, something I'm interested in is, are ERQs and red quasars two distinct populations, or are they kind of just extreme ends of the same dusty quasar population? And what we found is that if you compared the red quasars and the ERQs I just showed on the previous slide, how many of them satisfy the other condition? And when we do this, we find that 80% of the ERQs also satisfy our red quasar selection. Although this could be due to the fact we impose an optical selection in our target program. But if you compare that to the red quasars, kind of only, I forget the number, I think it's like 35% of the red quasars are also ERQs. So this could suggest that the ERQs might be a subset of the red quasar population, but we're going to explore the differences between the ERQs and red quasars and really kind of compare whether they're two distinct populations in our next paper. So now to just put it into context with SDSS, here I'm showing some different composites. So in the solid red and blue line are the red and blue composites from SDSS from our previous work. And in the dotted red and dotted blue lines are the red and blue composites from the DESI nominal program, so the kind of parent sample. And first of all, you can see that they're very similar to SDSS overall. But in black, we're showing the red quasars from our program, so the primary red quasars. And you can see that with our program, we're pushing to much higher levels of dust extinction, which again is what we wanted. Looking at the ERQs, in the dot dashed purple line, which is a little hard to see, we're showing the SDSS ERQs from the Heyman paper. And then in the solid gray line, we're showing the ERQs from the nominal DESI sample. And you can see they're almost exactly on top of each other. And something interesting about, or confusing, I guess, about ERQs is that you can see that they're redder than a typical blue quasar, but they're also bluer than this red quasar. And this is confusing because of the name, they're called extremely red quasars, but I'm telling you that on average, they're bluer than red quasars. And this is simply because, if you remember, ERQs are this weird optical to mid-infrared color cut. And just because you have a very red optical to mid-infrared color doesn't necessarily mean that you have a you're very red at the UV optical end. So you can have ERQs that have quite blue UV spectra, but then just have this very red and very bright mid-infrared colors. So they're a little bit different than the red quasars. But in green here, I'm showing the ERQs from our program, and you can see that they're almost exactly the same as the red quasars. Again, this is the fact that 80% of them also meet this red quasar selection. So you can see, you might see that there's potentially differences in the emission line properties. ERQs might have stronger emission lines, but this could be due to selection effects. And we actually have ex-shooter data of DESI red quasars and DESI extremely red quasars, which we've matched in luminosity, and we're going to do a study on the emission lines and dust reddening properties in more detail. So to quantify the amount of dust extinction we have in this program, we followed a similar approach to my 2022 paper, where we took a blue composite, we added some dust, and then we fit the DESI spectra. And this diagram is showing a histogram of the dust extinction values that we get out of this method. And in solid black are the red quasars from our program. And in the dotted purple, we can see the quasars from just the nominal DESI program. And what you can see is that on average, our program pushes to about 1.5 mags more in dust extinction compared to the average DESI quasar. Then just showing for context, in the shaded red, these are the red quasars we observed with ex-shooter in my previous paper, so SDSS selected red quasars, and you can see they're very, like I said before, very modestly reddened. So with DESI, we're pushing to these much more extinguished systems. So this green line is a lower selection boundary from the Glickman 2022 paper, where she uses a WISE 2-mass selection for red quasars, so a near infrared selection. So these are very reddened objects, but you can see that with our program, we're actually finding quasars that are just as reddened as these infrared selected red quasars. And similarly with Manda Banerjee's 2015 heavily reddened sample, again using a near infrared selection. These are very high levels of AV. Yet, even though DESI is an optical survey, we're still finding sources with consistent amount of reddening from these heavily reddened samples. Okay, so just to finish off, to link back to our earlier SDSS work, we wanted to look at the radio properties of these DESI quasars. And to do this, we used the LOFAR LOTS DR2 data, so 144 megahertz, or about 6 arcsecond resolution, but it's very deep, much deeper than some of the previous radio work we've done. And here's just showing the 6 micron luminosity versus the radio luminosity in 3 different bins of dust extinction, showing the nominal quasars and the primary quasars. And then in this dashed red line, we're showing the boundary for radio quiet and radio loud. And just to, if you're unfamiliar about like radio loudness, this is just a ratio of the radio to either normally the optical, but we use the 6 micron luminosity because it's less affected by dust extinction. So just a couple of things. As you'd expect, majority of the nominal quasars are in this lowest AV bin because they're very blue. The majority of ours are in this highest AV bin, and the majority of both samples are radio quiet. And this is because both DESI and LOFAR is pushing to these fainter magnitudes. So I think the most important plot of this talk and my paper, maybe my PhD, is this one here, where we're showing the radio detection fraction from LOTS DR2, but in bins of dust extinction. This is combining the primary and the nominal sample from DESI. And what we find is this strong positive correlation between detection fraction and amount of dust extinction. So this is saying that the more dust extinction you have in a quasar, the more likely it is to be radio detected. And just to make sure there was no biases from luminosity or redshift, we matched the objects in each bin in luminosity and redshift, and this is what this gray shaded region is. And we can see, although we're limited in source statistics, we still find this strong positive correlation. So this is suggesting our earlier work with red quasars, the whole reason why they had enhanced radio emission was simply because they had more dust, and which you can take directly from this plot. And then I'll just end on kind of looking to the future, pushing to more obscured things. A PhD student at Durham, Carolina Andoni, is comparing not only red and blue, but obscured versus unobscured quasars. So obscured quasars being having so much dust that you can't even see the accretion disk. And this is radio detection rate versus dust. And the important points here is the unobscured point in purple and the obscured point in this black square. And what she finds is that the obscured quasars are radio enhanced compared to the unobscured quasars, but they're also consistent with our red quasars, which would be classed as unobscured in her sample. So what this could be suggesting is there might be some sort of dust saturation point where this plot will eventually plateau out. So what I'm trying to say is that you're going to get to a point that even if you add more dust, you're not necessarily going to get more radio emission. And then just interestingly, she looked at the star formation properties and actually found that obscured quasars were enhanced the star formation rate compared to unobscured quasars, but then again was consistent with our earlier work showing red and blue quasars have no difference. So the fact that obscured quasars have the enhanced star formation might suggest that they're more early on in this evolutionary sequence, and more close to this starbursty phase, but then very quickly star formation shuts down once you get to this unobscured dusty red quasar. So in conclusion, we have a secondary target program in DESI, which has been shown to be very effective at selecting both red and extremely red quasars. With DESI, we're selecting red quasars with much higher dust extinction values compared to SDSS and the nominal DESI selection. And we're finding this strong link between the presence of dust and radio emission. So again, all of our results suggest that enhanced radio emission in red quasars, or quasars in general, is likely due to jets or winds interacting with dusty environment. We think dust or opacity is a very important factor for having radio emission in these radio quiet systems. So this is this possible interpretation that the red quasars reside in this more dust and gas rich environment. And we're going to test this wind versus jet scenario in upcoming studies. For example, one that we use UGMRT radio data, so 4-band radio data over 0.14 to 3 gigahertz, in order to construct radio SEDs to try and determine the origin of this enhanced radio emission. So thank you very much. I'm happy to take any questions.
Right, thanks a lot, Vicky. Are there any questions? While people gather their thoughts, I could ask a very probably silly question. Actually, no more questions. All right. Miguel, could you go first?
Yeah, this is probably a bit of a dumb question, but you mentioned how these red LRGs are more likely to have infrared emission, right? And you're mentioning that this is maybe due to jets. And my very dumb question is, why will we expect these like earlier quasars to have jets, more jets than the bluer later quasars, if that makes any sense?
Yeah, no, I probably wasn't clear that we're not saying they're more likely to. So first of all, we don't know whether it's jets or winds. That's notoriously difficult to determine, even if we're looking to get some like VLBA data. If you have very high resolution, you might be able to say whether it's a jet or a wind, or with this future UGMRT data. But if it was a jet, and the fact that it's very compact emission, that would suggest that the jet is very small. And this could either be because it's a very young jet, so jets grow over time, and the fact that we're finding that red quasars have a preference for very compact radio emission could be because the jet hasn't had enough time to grow, so it's in this younger phase. Or it could be because the jets are frustrated, so there's some kind of dusty medium that the jet slams into, and that causes shocks, which is why it's very compact, but they're more likely to be radio detected. And this would still fit in. Again, we haven't found any kind of conclusive evidence to say, yes, red quasars are definitely in this evolutionary sequence. We're just saying they have a lot of strange properties compared to typical quasars that suggest that they're intrinsically different in some way. But whether that's just because they happen to have more dust, or whether that's because they have more dust that's left over from this kind of merger evolutionary sequence, we're not sure. So I hope that answered your question.
Yeah, thank you.
All right, Adarsh.
Yeah, hi, Victoria, nice talk.
Hi.
So I have, so we, in some of my work and in my group, we look at these quasar absorption systems, which are intervening in the sense that they're not from the same host galaxy as the quasar itself. They're somewhere in between us and the quasar. And we're looking at these extremely strong H1 absorbers, and you can say other absorbers as well. And the property of these absorbers that are within or likely within the host galaxy, their host galaxy, is that they will have significant amount of dust. So I looked at strong H1 absorbers, which is called ESDLAs. And you can also look at, let's say, C1 absorbers by Siwei Zhu in her work. But what we find is all these systems will have significantly, or let's say relatively higher amount of dust than normal DLAs. Now, my question to you was, whilst you were looking at these quasars in the DESI or SDSS, we also looked at, so let's say DESI, and these extremely red quasars, did you happen to find, so my first question is, did you happen to find a large amount of strong absorbers in your systems, like DLAs and large DLAs? And whether do you think it is a possibility that the dust, or at least a part or a significant part of the dust, would actually come from these host galaxies rather than the quasar itself?
So that's a really good point. So what we found, first of all, in our X-shooter work, we did actually find a significant enhancement in the number of kind of magnesium. We were looking just magnesium 2 absorption,
yeah, okay.
and we found a higher number of the red quasars, which suggests that obviously a lot of these quasars, because we're only looking at a modest amount of dust reddening, they have this intervening absorber, it adds dust, then they fall into our selection. So there will be an enhancement, and there will be some quasars that are simply red because they have an intervening or an associated absorber. But we did do, I looked at SDSS, and there's somebody within DESI, maybe we could talk afterwards, who's looking at magnesium 2, I think it's Lucas, who's looking at magnesium 2 absorbers within DESI, and is compiling a catalogue within DESI of magnesium 2 absorbers. So I've asked him if he could have a look for us for our sample. He's been quite busy, I think, with his PhD thesis, so he's not got back to us. But I did look in SDSS, and I used I can't remember which catalogue, but I removed all the ones with intervening magnesium 2 absorbers, and I found, yes, there are a large, a fraction of the red quasars that are red because of these. But even if you remove them, we still find the radio enhancement. I think if anything, it gets a little bit stronger. So it's almost like these things are a contaminant. They're not true red quasars, but it's not a large fraction, and we find it doesn't affect our results much either way, even if you remove them. If that answers.
On that note, sorry, if you give me 1 second, could we go back to that plot that you showed of the combined spectra of all the extremely red quasars versus the ones? So I mean, I can't help but to slide 4 maybe, or even this one. Actually, I can't help but notice. I mean, it could be just nothing, but if you see in the Lyman alpha of your non-reddened as opposed to the red, which is the black line, I assume, I do see absorption, and again, as I said, this is might not be true absorption, because there's a similar kind of sort of absorption that I see in the noise itself after the Lyman alpha and others. So, but I was just, it would be interesting to see, that's all.
This could also be, like I said, we have this link to Bal quasars, so you're more likely to have a broad absorption in red quasars. But again, we did it's not published yet, it's still in prep, but we did a little study where again in SDSS, and I'd love to repeat it in DESI, where we removed all the Bell quasars from our red quasar sample. Again, we found there was a higher fraction compared to the blue, but when you remove them, we still find this radio result. So it's because a lot of people thought, oh, maybe you've got this high Bell contamination, and Bell quasars are known to be radio enhanced. So maybe that's just driving your results. But even if you remove the Bell quasars and the magnesium absorbers, we still find this difference, which is suggesting that it is really kind of dust or opacity that has this link with the radio emission. But yeah, it can be quite difficult to disentangle all these different things. And it would be cool to do like a short paper on absorbers in red quasars, even just to say, look, you don't need to worry about it. It's not a problem. That's, we've been thinking about that.
Thank you.
Right. Are there any questions? If not, I can conclude the talk. Yeah, I can ask my own question later.